When we look up at a cloudless sky and see a random leaf drifting down, it feels as though the world is simple. Everything moves downward because there is gravity. We grow up with the sense that gravity is almost a banality, a familiar background presence of everyday life. Yet behind this familiarity hides one of the most dramatic mysteries of science. Modern physics argues that what we call the force of attraction is not truly a force in the ordinary sense. It is the result of the bending of the universe's very fabric, what Albert Einstein called the space-time continuum. However, 20th and 21st century science has run into a dead end. If electricity, light, or even the interactions of atoms can be explained in terms of carrier particles, then why should gravity be an exception? And if all the other forces have their own particles, then there must also exist particles of gravity. They are called gravitons. Yet here lies the paradox. To this day, no one has ever seen them. This enigma has captivated scientists for almost a century. One of those who dedicated his life to seeking answers was the American physicist Kip Thorne, Nobel laureate in physics and one of the creators of the LIGO project. It was this giant laser interferometer that first detected gravitational waves. The task had seemed impossible because capturing the faintest ripple in space-time is like trying to perceive the trembling of a spider's thread in the whirl of a hurricane. And yet, it was achieved. Now the question arises, if we have managed to hear the song of gravity in the form of waves, can we capture its individual notes in the form of gravitons? Thorne himself wrote that the discovery of waves was only the beginning, a direct path toward a new reality where space and time will cease to be abstract words and become something tangible. Philosophers in antiquity already said that what is invisible to us does not cease to exist. Lucretius claimed that the world is woven from unseen particles. Later, similar ideas became part of quantum physics, but unlike the particles of light, which we call photons, gravitons stubbornly remain ghostly and elusive. One of the modern explorers of this mystery, the British physicist Roger Penrose, reflected on the structure of space and concluded that reality itself may not be what we think it is. His theory of conformal cyclic cosmology suggests that our universe can be reborn again and again, and in this endless rhythm, gravity plays the central role. Penrose's theory, which he called conformal cyclic cosmology, may sound complex, but it can be explained simply and vividly. He proposed an unusual idea. Our universe has neither a single beginning nor a single end, but lives in repeating cycles. He calls these cycles eons. Each aeon has what we think of as a Big Bang, and what we imagine as the ultimate fading of the universe. But the end of one aeon smoothly becomes the beginning of the next. How can this be? The key is that Penrose claims, when the universe grows old and cold, there is almost no matter left within it, and what remains are only photons, particles of light with no rest mass. In this state, the distinction between enormous and tiny, between long and short, simply disappears. For photons, there is no scale. They behave identically in the infinite vastness and in the tiniest speck. Thus, the final state of the old universe can be viewed as the new beginning, as another Big Bang, but for the next eon. This creates a striking image. The universe does not live and die just once, but like a breath, shrinking and expanding again and again. Gravity here plays the fundamental role because it shapes the fate of matter, of black holes, and of the cosmos itself. According to Penrose's calculations, it is precisely the evaporation of black holes and the transition to a purely photonic universe that makes such a rebirth possible. Let us return to gravity. Imagine the fabric of a carpet onto which a heavy stone falls. At the point of impact, a depression appears. If you roll a small ball nearby, it will roll down toward that hollow. This is the example most often used to explain Einstein's vision of gravity. But if we look closer, a question arises. What is the carpet itself made of? When scientists speak of quantum gravity, they try to understand not only the shapes of the depressions, but also the very threads from which the carpet of space-time itself is woven. Here arises a sense of mystery, because even the brightest human minds collide with the enigma, as if space and time slip through their hands like water. It is in moments like these that science ceases to be a dry set of formulas and becomes a human drama. Scientists argue, spend decades searching, make mistakes, sometimes lose faith, and then start all over again. Within this struggle lies something profoundly inspiring. And if you are interested in stories such as these, please support our channel by subscribing, because ahead lies an even more fascinating conversation about the frontiers of science. When Einstein proposed to think of gravity not as a force but as geometry, he overturned humanity's notions of space and time. But the advent of quantum mechanics posed a new challenge. The micro-world is arranged differently. Laws of probability, superposition, and entanglement operate there. And when we try to combine quantum theory with the general theory of relativity, it is as if two languages collide that refuse to become a single text. On one side, we have Einstein's continuous and smooth spacetime, and on the other, the discrete, sometimes chaotic world of quantum particles. And the main question of the century arises: can there exist a particle that carries gravity? That particle is called the graviton. However, here lies a huge difficulty. According to calculations, the graviton must be incredibly light, almost weightless, and interact so weakly that no known detector can catch it directly. American physicist Steven Weinberg, Nobel laureate and one of the creators of the Standard Model of Elementary Particles, said that searching for the graviton is like searching for a ghost in a hurricane. It is everywhere and nowhere at the same time. Mathematics strictly states that without the graviton, quantum field theory would be incomplete. But physics encounters the limits of experimental capabilities. Science history knows situations where a particle was predicted long before it could be caught. The electron was discovered by experiment, but the neutrino remained only a hypothesis for decades. It is important to stop and clarify. Neutrino and neutron are completely different particles. The neutron is a large particle inside the atom, while the neutrino is tiny, almost weightless, passes through matter without difficulty, and is practically undetectable. Thus, the neutrino had to be literally scraped out from space to confirm its existence. So the hope for the discovery of the graviton is not unfounded. Some researchers, like John Donohue from the University of Massachusetts, believe that at some point, quantum experiments at accelerators will give indirect traces of these elusive particles. The philosophical aspect here is enormous. If the graviton exists, then space and time are not a continuous smooth stage, but tiny pieces of woven fabric created by billions of such particles. This means the familiar world, with its ticking clocks and horizons, is actually born from quantum pulsations. And in some measure, we live inside a gigantic musical instrument where each note is a quantum, each echo a gravitational wave. Take a simple observation. Stand barefoot on the ground, close your eyes, and feel the weight of your body. This sense of attraction seems obvious, but to a physicist, it is a signal from the curved fabric of the universe. If gravitons exist, they penetrate all space, including your body and the earth beneath your feet. One could say that through each particle of your body continuously flows a huge stream of these quanta, which create what we perceive as gravity, the force of attraction of the earth and other bodies. It is like the air around and inside us constantly filling with gas molecules. We do not see or feel them directly, but thanks to them, we breathe and feel pressure. Similarly, gravitons do not coat the surface of the body, but continuously penetrate and interact with it on the level of fundamental forces. This process is akin to breathing. We usually do not notice air entering and leaving the lungs, but become aware of it when paying special attention. Similarly, we can say gravitons are inside us and surround us every second because they are linked to the very structure of space-time that supports gravity. Therefore, when you lift a cup or move, you are not just moving through empty space, but interacting with its structure, whose core may be these quanta, gravitons. Your body and the earth are connected with them as a musician is connected with the sounds he creates. At this point, it is worth taking a small freeze frame. If the idea that our world is much more mysterious than familiar school formulas resonates with you, please like this video. This will help spread the conversation about the great questions of science and philosophy that rarely come up in everyday life. But while we ask this question about the graviton, scientists have made another step that may change the very foundation of physics. This is the holographic principle. The idea was born from reflection on black holes. Physicist Jacob Bekenstein, back in the 70s, suggested that all information about a body falling into a black hole is somehow preserved on its surface. Later, Dutch physicist Gerard 't Hooft developed this thought and formulated the hypothesis. Perhaps the three-dimensional world we live in is actually a projection, a hologram encoded on the surface of some deeper reality. This idea sounds like a plot from science fiction, but many take it seriously today. And it becomes especially acute in the context of gravity. For if the world is indeed holographic, the graviton may not be a particle existing in our space, but a shadow of something more fundamental. Then, the very question of its search becomes a door to a different understanding of reality. At first, the idea of the holographic principle sounded so daring that many considered it almost metaphysical. However, this is how science works. Radical hypotheses sometimes turn out to be the only way to break through walls of contradictions. American physicist Leonard Susskind, one of the leading theorists of string theory, developed 't Hooft's view and initiated an entire new era of research. His books and lectures have made the hypothesis of a holographic universe not just a scientific guess, but a fully fledged direction in modern cosmology. Imagine a familiar hologram on a credit card. When you look at it, you see a floating three-dimensional image, although it is entirely encoded on a two-dimensional film. Susskind claims that our universe is arranged the same way. All the information about events inside, including galaxies, stars, and even your thoughts, may be recorded on the boundary of the cosmos, as if we live inside a volumetric picture arising from a thin film at the edge of existence. At first glance, this sounds incomprehensible, but it is precisely the holographic principle that allows quantum mechanics and general relativity to be reconciled. When scientists applied it to black holes, they found an unexpected answer to the question tormenting generations of physicists. It seemed that any particle entering a black hole disappears irretrievably, violating the law of conservation of information. However, if information is preserved on the surface of the event horizon, the contradiction disappears. This thought so inspired Susskind that he compared working on black holes to a journey to another world. He said that the very nature of reality is hidden in the code that operates on the boundary of the universe. If this is true, then we live in a colossal holographic series where every page of the script is stored on the surface, and what we see in 3 dimensions is only an illusion of depth. German philosopher Immanuel Kant, in his Critique of Pure Reason, argued that space and time are merely forms of human perception. Modern physics seems to confirm his guess, only now in the language of mathematics and experiment. Research in quantum gravity and the holographic principle unexpectedly brings us back to old philosophical questions about what is real and what is only an image in our consciousness. To feel this yourself, try a simple thought experiment. Close your eyes and imagine the entire cosmos, from the nearest trees to the distant stars. Now try to picture all this infinity recorded on a thin boundary, like a film on a bubble that surrounds you. The feeling is strange and even a little unsettling, but it conveys the scale of the ideas on which the best minds of our time work. A curious fact is that the hypothesis of the holographic universe received indirect support from computer simulations. American physicist Juan Maldacena in the late 90s showed, through the example of the so-called ADES-CFT duality, that quantum theory can be linked to a theory of gravity in higher dimensional space. This meant that the mathematical code describing microparticles can be reflected in terms of curved space. His work is still considered one of the most cited in physics and inspires generations of young scientists. Imagine you have a 3-dimensional world contained inside a volumetric sphere, and all the information about this world is recorded on its 2-dimensional surface like a hologram. At the same time, complex processes inside the sphere are simply and clearly described from the outside by the information on its surface. It is like studying a complex ocean without diving into it, but observing changes on its surface, which contains all the necessary information. Or consider another example. Imagine a game with a three-dimensional world. Say, a video game where a character runs, jumps, and fights. In fact, this three-dimensional world is controlled by code, a set of simple rules and instructions that look nothing like the game on the screen. This code is like an instruction written on a flat piece of paper. Now imagine the entire volumetric three-dimensional world in the game is the universe with gravity and space-time, and the code on the paper is a simpler theory describing the same but in another, flatter form. 8S CFT duality is like opening the instruction from a flat sheet and understanding how the three-dimensional game is arranged. That is, one theory, which seems to describe a simple two-dimensional world, actually contains all the information about the three-dimensional space with gravity. It's like a hologram where a flat surface records a volumetric image. In real life, when you look at a hologram on a plastic card, you see a volumetric image, but the information is recorded exactly on a flat film. Thus, physicists use this connection between simple and complex to solve the riddles of the universe and try to unite quantum mechanics with gravity. One can imagine that studying the invisible laws of the cosmos is like solving the mysteries of a huge game where every line of code is important for a complete understanding of the whole world. And although the idea itself seems incredible, it offers hope to explain what so far resists unification. For if our three-dimensional world is indeed a hologram, the graviton may be a mathematical stroke of this code, an elusive note heard only in harmony with the whole orchestra. Therefore, it's especially important to share these ideas, argue, ask questions, and reflect. And your thoughts on whether our world could be a hologram will be invaluable. Write about it in the comments. Perhaps it is in discussion that the energy that drives science forward is born. The history of science is always full not only of formulas, but also human destinies. The question of quantum gravity revealed a contradiction between two giants of the 20th century, Albert Einstein and Niels Bohr. Their debates about the nature of reality became legendary. Einstein, convinced that the world obeys strict laws, could not accept the probabilistic magic of quantum mechanics. His famous phrase that God does not play dice reflected this resistance. Bohr retorted that one should not tell God how to run the world. The debate lasted decades and became a symbol of the struggle between two worldviews. In the mid-20th century, new voices joined them. American physicist John Wheeler, Kip Thorne's teacher, introduced the term black hole into science and claimed that space-time is dynamic and can behave like a living being. Wheeler loved metaphors and said the universe is a self-questioning creation. He believed quantum gravity would inevitably reveal the mystery of the origin not only of the world but also of consciousness. Stephen Hawking, drawing on the ideas of Wheeler and Penrose, proposed a radical explanation. Black holes emit radiation. This contradicted intuition, but calculations showed that quantum effects can cause the event horizon to emit energy. This was the first window to uniting quanta and gravity, but along with it arose the information paradox puzzle. If a black hole evaporates, where does all the information about what fell inside go? This inspired the development of the holographic principle. We must not forget the dramatic fate of those who went against the current. Jacob Bekenstein, still young, faced harsh criticism when he proposed the idea of entropy and black hole decay. His papers were rejected, he was accused of mistakes, and only years later was it recognized that he was right. Today, his name stands alongside the greatest minds in physics. This story reminds us that truth often comes at the price of doubt and loneliness. Modern debates are even more intense. Roger Penrose, in his book The Road to Reality, asserts that space-time may not be a smooth canvas but a complex pattern where quantum effects and gravity interweave in geometric forms. His concepts of a cyclic universe sparked much controversy but earned him a Nobel Prize for discoveries in black hole science. For all these scientists, the search for the graviton is not just a technical question. It is almost a spiritual challenge, the aspiration to understand what existence itself is made of. When we read their biographies, we see not only lines of accolades, but human faith, persistence, and greatness of spirit. Their hours stretched in calculations and endless discussions, and our hours today run thanks to their courage. Every great scientific discovery has two sides. One faces the world of formulas, laboratories, and instruments. The other faces our inner space of questions and meanings. And when we talk about gravitons, we speak not only about fantastically tiny particles, but about what can reshape our understanding of reality itself. If the existence of the graviton is confirmed, the entire picture of the world we are used to will prove to be just a fragment of a deeper and more complex symphony. Then every second of life will gain a new dimension. An ordinary step on the street will become an interaction with invisible quantum particles that link your body with the Earth and distant galaxies. The familiar falling stone will turn into an invisible dance where tiny gravitons coordinate the movement of matter billions of times per moment. We will witness that the familiar physical world is only one facet of a vast and profound universe. But if it turns out that gravitons do not exist, that will not be defeat either. It will open a new horizon, a sign that reality is arranged even more amazingly than we could imagine. Physics always advances step by step, refuting the old and creating the new. And this journey is like a journey without end. As philosopher Soren Kierkegaard wrote, "Truth is a path, not a final goal." The most important thing is that we live in an era where these great quests happen before our very eyes. Never before has humanity been so close to mastering the language of the universe itself. And maybe it will be our children or grandchildren who first speak directly with the cosmos. To feel this for a moment, try going out at night under the open sky, look at the stars, and remember that your gaze pierces through millions of light years. At the same time, every cell of your body obeys the same laws of gravity that gave birth to galaxies. When you see the dark sky, it is not just emptiness, but a vast continuum where your very thoughts also reach somewhere. That is why science is never limited to the laboratory. It always penetrates the heart of a person, making us ponder meaning and the future. Perhaps when a theory of quantum gravity emerges, we will learn not only what space and time are made of, but also find a new perspective on the very phenomenon of life and consciousness. Support this conversation with a like if this view of science resonates with you, where formula and philosophy walk side by side. And if you subscribe to the channel, together we will continue this journey, where each new episode will be a step toward answers to the deepest mysteries of the universe. And of course, share your thoughts in the comments, for it is precisely your reflection on what space, time, and gravity are that makes this conversation real, alive, and endless.